the application we're talking about here is something called danceroom spectroscopy, which originally started as a public engagement project. And so when you're going to go to a conference on many-core processing, the first thing you do is you get a many-core laser pointer. So I hope everyone can focus on everything in this presentation at the same time, because this is the kind of way that you have to think about these kinds of problems from what I've gathered in the talk so far. Anyway, no, I'll go back to more conventional laser pointing now, but I've always wanted to make that joke, so I could see how tough of a crowd I'm up against. Okay, so it's danceroom spectroscopy, and it's an interactive system for doing quantum molecular dynamics accelerated on some GPU architectures using OpenCL. That's what I'm going to talk about. I'm really delighted that Andreas started his talk with a quote by Richard Feynman, because actually the physics that runs the stuff we're going to talk about is built on a formulation of quantum mechanics called path integral quantum mechanics, which was something that Feynman dreamed up. So I thought it was really cool that we started off with the Feynman quote. Feynman's great for quotes. I mean, it's hard not to find a Feynman quote. So I'm going to just tell you a little bit about the background of what danceroom spectroscopy does, which we abbreviate DS. I'm going to tell you a little bit about what we've done with it, where it comes from, how it works. I'm going to say something about the underlying mathematics and algorithms. And I'm going to focus on computational expense, so that when I tell you what we've done with the GPUs, it kind of makes some sense. And I'm going to tell you a little bit about the hardware and software that runs danceroom spectroscopy. And I'm going to tell you about how careful selection of those parts of danceroom spectroscopy to GPU accelerate enable us to save the host for doing a bunch of other stuff that we never imagined was possible. And then I'm going to speculate a little bit on where this could go. As I said, it started as a public engagement project, but it's kind of starting to take on a life of its own. And I think some really interesting scientific questions are starting to emerge for what we could do with it. And then at the end, we're going to run it. I'll give you a short little demo with my favorite feature of the system. I'll generate a soundscape for you using a real-time Fourier transform that comes from interactive quantum dynamics. It's really cool. And then we're going to leave it running over lunch, so that if anyone wants to wander in and have a look before the next session starts after lunch, then feel free to come in, and we'll be here, and you can see how it all works. Our whole setup's over there. So before I start, I just want to say that this project involves a lot of people. There's a number of collaborators. Phil, too, did a lot of the programming. Simon McIntosh-Smith and one of his PhD students, James Price, are the many-core gurus that we've collaborated with to get us really starting to wrap our heads around how to think about parallelizing this code and efficient implementation strategies. And then there's a number of artists I've been involved with. So Tom Mitchell is sitting over there. Laura Kriefman is a choreographer who's in the audience, who's been using this technology as an artistic tool. Becca Rose, and loads of other people. And whenever I show this slide, I always like to say, spot the chemistry professor, because I think it's fairly obvious which one he is. So a big emphasis on this project compared to some of the other things that we've heard about today is portability. Okay? So effectively what we've built is we've built a 360-degree interactive high-performance computing system. But we don't have the luxury of a massive supercomputer, so we have to have something that's relatively small that we can carry and take with us to go places. So for example, here's everyone's favorite logo. We did this at London 2012 in a 360-degree projection dome. So this is a path integral quantum mechanics simulation. It's actually really hard to photograph this, because we're only using conventional cameras. We built this complicated 360-degree technology, and then we can't actually take a photo of it because we didn't build the corresponding camera to take a picture with it. So I can never really show people what it looks like unless you're in there. I'll explain to you a little bit how the 360 technology works as we move on. So we did it at the Olympics. Just 2 weeks ago, we had a headline event at the Barbican Arts Center in London, where we used this kit to run a dance show. So I think we have probably the world's first ever attempt at choreographing quantum molecular dynamics. And you'll see a little bit of how it works near the end. The show is called Hidden Fields. And as you might gather from this photo, the gender balance of Hidden Fields is slightly different than the gender balance in this room. This is a shot from the performance at the Barbican, just to give you a sort of idea of what it looks like. But it was cool to have somebody who's a chemical physicist be involved in a headline art event at the Barbican is a really fun thing that the opportunity doesn't come along very often. It's super fun to do that. So just to tell you where danceroom spectroscopy came from, and then I'll move into how it works. My job is running molecular dynamics in any of a variety of flavors, from classical to semi-classical to fully quantum. And I study everything from fundamental quantum mechanics of gas phase interactions that would influence things like air pollution, climate change, to larger bulk things. So this is a simulation of diamond. And so I spend a lot of my day generating complex data that then gives you movies. And I've watched these movies now for, what, 5, 6, 7 years? And I always think it looks like the molecules are dancing. Okay? Now, there's some really interesting physics that you can analyze that comes out of a solution of this. But this is what diamond's doing right on a molecular level. And so I always thought, it looks like it's dancing. And so when I explain to people, I say, yeah, I study dancing molecules for a living. So as a lot of you probably know about, the way that molecules and atoms dance depends on the energy landscape that guides their molecular motion. The energy landscape is effectively a force map, right, of all the different interactions that that an atom and a molecule experiences over the entire possible conformational space available to it. So I have a very simple schematic of an energy landscape in just 2 dimensions, right? And we've applied this to understand some interesting problems in quantum biology, for example. I have another 2D energy landscape, which shows a more interesting topology. And this is actually calculated from extremely sophisticated quantum simulations. So we actually solve the Schrodinger equation to generate this kind of a map. And you can really learn interesting things about what molecules do and how they behave from generating these kinds of maps. So energy landscapes are a fundamental metaphor in modern physics. They guide thinking across chemistry, biology, even people that do particle physics think about energy landscapes in every single domain of modern science. It's really becoming an important metaphor. So the questions that sparked DS, there's like the pie in the sky question that really sparked DS, and then there's the practical questions that you tell people when you write papers spark DS. The pie in the sky question is, you know, could I step into a molecular dynamics? Wouldn't it be cool if I could step into a molecular dynamics simulation? I spend all my time doing it. It would be really fun to literally become a field myself and then play with it. Practically, though, there's an educational angle to this very much, as well as an HPC angle. So the energy landscape metaphor is fundamental to modern science. Is there a mathematical framework for turning this idea into fast algorithms that could facilitate an interactive experience? Okay. Number 2 is, even if we have the algorithms, can we actually build a portable HPC system that's compact enough to take it around and show it to people? And then the third thing is, can we use it to fuel an engaging aesthetic experience, right? That also can be used as a teaching tool. So can I actually use it when I do my lectures to undergraduates or at schools to teach them about molecular dynamics in an interesting way? Before I launch into all the algorithms and math that we use, I have some funny observations. So when you take science that is detailed written and you spend your life thinking about it and you just put it out there for general consumption, you just get all kinds of crazy responses. I don't know if anyone has this experience. I have a few here. So, I mean, they kind of go from the more sensible to the more ridiculous. I have a continuum. So the Institute of Physics did a story on it in Physics World called Dancing in the Quantum World. Chemistry World, which is the Royal Society of Chemistry, did a molecular dance set to make waves across the pond. We were invited to go talk about some of this at South by Southwest Interactive Festival in Austin. Qualcomm commissioned me to write about it. I did a piece called Escaping the Uncanny Valley. They were fascinated in video game representations of people not as characters but as fields. The Creators Project did a story, Danceroom Spectroscopy lets you party in the subatomic world. Okay, so you can see it's getting more ridiculous. This is some website called The Engineer. 3D Imager shows how particles interact with energy fields. Okay, I guess. EPSRC did a story. dancing the time warp in the quantum world. I talked to the woman who did this, and I said, I really don't understand what time warp has to do with what we're doing here. And she said, well, I'm a really big fan of the Rocky Horror Picture Show, so I really want to put the time warp in there. I said, I don't even know what the Rocky Horror Picture Show is, but whatever. So Beyond Dance, Dance Revolution was a South by Southwest title for something that we did. Microsoft covered it, right? What's part video game, part science visualization, part art installation, part social experiment. Some guy called it the Nano Dance, which is a name that I quite like. And then the funniest one of all is I did a lecture for the undergraduate society at Bristol, and they wrote up and they said, can only be described as quantum chemistry on LSD. And no LSD has been consumed in the making of this presentation, I can assure you, okay? So the hardware setup that we use lives right over there. We have basically a little workstation that we just crammed as many GPUs as would fit in there. There's some specs here. So it's got an Intel i7 hexa-core hyper-threaded CPU, which has a liquid cooling system, so it's overclocked to run at about 4.6 gigahertz. We've got a total of, it's got 4 inbuilt USB hubs, not sockets, actual hubs. Plus we have a PCI extender card, which allows us 4 additional USB 2.0 hubs. It's got 2 slots for dual GPUs. So we've experimented with NVIDIA GTX 590s as well as Sapphire Radeon HD 6990s. And what happens is the system that we use to kind of realize this, so this, I'm telling you, this is the ideal system, and then I'll tell you about the challenges we faced in the remainder of the talk. The idea initially was we'd have a person in a space. Actually, we can have arbitrarily large crowds of people in a space. We have some depth sensors that are going to be imaging them, taking depth matrices of the space at 30 hertz capture rate. They're going to send the depth matrix to our GPU workstation. Our GPU workstation is going to be running this quantum molecular dynamics simulation with a certain field that represents the internal forces acting on the molecules. And then the GPU workstation is going to interpret that depth data as an external field that acts on the whole system, dependent on people's motion in the space. Okay? So it's literally interpreting people as force field imprints. All right, then we do a bunch of graphic stuff. We send it to projector in the space. People can, when they come in, can see the real-time effect on the simulation. And then we do a bunch of analysis on the data using a bunch of tricks from molecular dynamics that I'll talk about in a second. And we get a bunch of data sets that we've collaborated with musicians. What kind of data could you make beautiful sounds with? We've kind of settled on some good strategies. We ship that into OSC, send it out to another laptop running Max MSP in Ableton, and then the musicians in real time can actually sonify that data with a suite of tools that they have. So that the net result is people in the space are generating in real time the graphics and the sounds that they hear by the motion of their force field perturbation interacting with this MD simulation. The sensors we use is this little contraption that I have right here. We can run, in the Olympics, we did full 360, so we could actually run 7 at one time. So we actually had a full 360 adapted thing, which was pretty awesome. Here we're just running 3, okay? And so we've also used Microsoft Kinects, but we like these for some more technical reasons. So this is how I initially imagined that DS would work. I thought we would take depth matrix, right? And we would interpret that literally as a 2D energy landscape. And so I have here just a velocity Verlet algorithm. Velocity Verlet algorithm is derived from a Taylor expansion. It's a good algorithm for propagating classical equations of motion. It's accurate to third order in time. And critically, the velocity Verlet algorithm depends on the forces, right, that are acting on each particle in the system. So I partition the force components in DS, so the total potential energy. So you see the force is the opposite of the gradient of the potential energy with respect to the coordinates. I partition the potential energy into the internal energy component and the external energy component. And so basically I can simply split it up here, right? So I have 2 force components, internal forces, external forces. The internal forces are going to come from some sum of pair potentials over the whole atomic ensemble. Okay? And so for this, we use something called a Leonard-Jones force field. This is a simple force field that was actually developed in Bristol in like the 1940s. That is still a standard model for how people that study condensed phase physics think about liquids, for example. Most importantly for our application, it's a cheap way of testing things, right? We don't want to blast in the most complicated force fields. We know how to do that, but we didn't want to start with that. So we have the internal force field is this liquid force field, okay? So there's slightly a little attractive well, so sometimes you get a little clustering, but it's mostly repulsive. And then the external field basically comes from evaluating the position of the particle on the depth matrix from the 3D capture system, okay? So that's how I thought it would work. But stupidly, I've only ever worked with systems that are closed systems where the first law of thermodynamics works. Okay, you generally, as a scientist, first law of thermodynamics is pretty good, isn't it? So, you know, normal mechanics starts by writing a Hamiltonian energy function. So you have some kinetic component, some potential component, and that is constant for a closed system. In DS, it's not closed. If you have a little kid standing still in the system who starts jumping, they're adding energy into the system. And the numerical integration of the equations of motions just blows up in your face. So we really struggled with how to deal with that, because when we first wrote it, we were just getting it would be stable. A little kid would move around, like shake their arm or something. This whole simulation blows up. So we have to basically enforce a thermostat. So we force a thermal temperature distribution on the whole simulation. And what we did is we used something called a Berenson thermostat, which basically says there's a decay rate down to the equilibrium temperature at some rate, with some time constant that I can specify. And we can specify that time constant in real time on the software. The most important thing we found is we had to make an important modification, because the things that really killed you were little tails in the Maxwell-Boltzmann distribution in the velocities. So if a kid would just make one particle wiggle, and that energetic particle takes off and blows up everything, your equations of motion just blow up in your face. So we had to do an algorithm where we search for the outliers, and we enforce those back into the equilibrium distribution, and that worked really, really well. The other problem, so this is actually why we use quantum mechanics and not classical mechanics. This is kind of interesting. We use pretty cheap 3D sensors, right? And they're noisy. So you're getting these depth matrices back, 30 hertz, but the oscillation in the depth matrices is significant. And it's so bad that it actually inhibited the interactivity. So you're trying to interact with this dynamic simulation, but what happens is the particles are just oscillating, doing Brownian motion in the stochastic noise of the depth matrices that are coming back. So what do? So we basically invoked what's called a semi-classical approximation. So there's a physicist at Harvard called Eric Heller, and he has a pretty seminal paper from back in the 80s. It says it's called Frozen Gaussians, a simple semi-classical approximation. It's a way of approximating quantum effects in a classical system. And basically what you do is you represent your particle. You don't represent the particle's potential energy simply by its point position in space, as you would in a classical model. You represent the potential energy the particle feels as some blurred wave, little Gaussian wave packet in that local space. And so you're basically averaging over the noise in a way that gives you really gentle, nice, smooth, intuitive interactivity. And that was really the reason we used this quantum approximation. Okay, so you see I now represent my potential as this integral over a two-dimensional integral over some Gaussians, and that Gaussian has some width parameter. And to derive that width parameter, I use Feynman's famous path integral equation, where you can actually derive that width parameter for a thermal ensemble of atoms. And that gives you what the average quantum width is from the Heisenberg uncertainty principle. So that's our width. So our width actually depends on the temperature of the simulation, which we can control in real time. And so Feynman Hibbs wrote this really famous book here, Quantum Mechanics and Path Integrals. So that's why I was pleased that Andreas started with Richard Feynman. The other thing we do is we have a bunch of sonic tricks, okay? In real time, we analyze collisions of the particles, so a real-time collision detection algorithm. And then we can take that data and we can send it to the electronic musician to sonify in whatever way they choose. It's got event tags and event triggers. We also fast Fourier transform the ensemble average velocity autocorrelation function in real time. So what this is it's basically a moving time history of how all the velocities of the system depend on some previous point in time. So how does that velocity vector project on some previous time point? And so you move that history forward in time, and if you Fourier transform it, you get all the characteristic vibrational motion in the system. So as you'll see at the end, I'm going to vibrate, and it's going to pick up my vibrational frequency, and then it's going to phase lock my signal based on that. And the sounds you're going to hear are actually going to come from this Fourier transform. And then we were able to write a really fast peak picking algorithm that basically does analysis of the vibrational spectrum. There's another sonification algorithm we have, and because I know that we're close to lunch and we ran over, I'm not going to go through all the detail of this, but I've been calling this algorithm the stochastic evangelical conversion algorithm. And the reason for that is because we think it's basically a dynamic grouping algorithm. So it can detect transient particle clusters in real time. And the way that it works is we give each particle 2 data pieces, a group ID and a membership kernel. Okay? So the kernel is basically amplified by collisions with particles that have the same group ID. So the particles feel a stronger sense of belonging to their group. Right? The kernel is attenuated by collisions with particles that have different group IDs. So if a guy from one group meets a guy from another group, then they both become less confident in what they believe. And then the kernel has a characteristic decay time scale. If there's no interactions, he kind of just decays into like complete agnosticism. Okay? And particles with strong membership kernels that can convert other particles. So if a guy that really believes something strongly meets a guy that doesn't believe something strongly, there's a stochastic probability he can convert that guy into his group. And this actually works pretty well. And this is something we couldn't dream of doing before we did the GPU acceleration. That's because you're going to see the simulation in the demo, but this is all being run by an invisible additional quantum dynamics simulation that you can't see, which is going on all the time just to do the real-time group tracking. And that requires about 500 particles, which we couldn't even dream of doing pre-GPU. And then we can map the average properties of the group, so their average centroid velocity, their centroid positions, and a number of properties, and we can sonify those. So the global system execution loop is basically schematized here. We get our depth matrix. We have to subtract the background, so we check if a background is available. We calculate the external forces, the internal forces. We propagate the system forward. And then if we want sonic output, we can go through any of this strand of the flow chart here to do any of our sonic tricks. Okay? And then we do all our graphics rendering, and we just loop around propagating equations of motion this way. So why did we have to do the GPU acceleration? Well, we had to do it critically for London 2012. So I told the University of Bristol that if they gave me 40,000 pounds, I would put DS at the Olympics. I didn't know anyone at the Olympics, and I didn't even know if the Olympics would be interested. But somehow we managed to do it. We managed to find these guys that had a 360-degree projection dome, and we said, we can put our stuff in there. But the problem was that the specs we had to meet were pretty intense. So when we did it in Bristol, at the Art Museum here in Bristol in the summertime, we had to fill up particles on 48 square meters of screen space. We ran 3 3D capture cameras at 30 hertz. And we only had to render across 1 graphics output at 60 hertz. In the London 2012 dome, we had to fill up 130 square meters of screen space. We had to run 7 3D capture cameras at 30 hertz. And we had to seamlessly render the graphics across 5 outputs at 60 hertz. So we couldn't do that with just our CPU-only technology. And so we've experimented with both NVIDIA GPUs as well as AMD GPUs. OpenCL was critical to this because we could swap things in and out and chop and change, and our code ran on both of them. So that really helped us a lot, especially at crunch time 2 days before we're supposed to do the show, and we realized that we needed to add a new graphics card in there. So I just said something about OpenCL. So for a lot of people in this audience, the OpenCL structure is going to be fairly well known. Simon is the expert in how this works. But this is basically the OpenCL programming structure. You have some hosts, splits things up into OpenCL devices. Within those devices, you have compute units. And then within those compute units, you actually have your processing elements. And as people here know, the critical bottleneck is shipping things from the devices to the host and back and forth. So the DS code we've written it in C#, actually, which is kind of surprising that it works. Okay, it's about 50,000 lines of C#. We use the Clue C# wrapper. So Clue is written by the guys that are responsible for Mono, which is a cross-platform .NET framework. And it actually works extremely well. This whole thing you're seeing is running on Windows, remarkably. I never thought this would have been possible, but Phil convinced me this would be possible, and it actually works. So there's C# wrappers to interface with OpenCL, and they bolt right into Visual Studio. To do debugging, we use IBM OpenCL libraries. And we actually did the debugging by running the OpenCL on the CPU to do all our printfs and debugging. So once we knew it worked on the CPU structure, because we had that hexacore hyper-threaded thing, then we could run it, we ported it to our GPUs. And so, as I said, OpenCL was really critical for allowing us to switch between different GPUs and test out what worked. And that was actually critical, mostly because different GPUs have different number of graphics outputs. And we had to render across so many graphics displays that we really actually, in the end, had to go with the AMD one simply because the number of graphics outputs it has is larger than the NVIDIA one. So after we did the CPU to GPU conversion, we got a pretty dramatic speed up. We could cope with 7 3D sensors. We could do rendering across 5 graphics particles, 5 graphics outputs. And we could, instead, we were only able to do 300 quantum particles, and we were able to go up to 10,000. So that 500 particles that we need just to do the invisible sonification stuff that you're going to see in a second was totally impossible before we did the GPU stuff, right? We couldn't have even dreamed of doing that. But now we have all these spare particles. We don't actually need all 10,000. We can do other interesting physics stuff under the hood. So very briefly, the parts of the system that we're accelerating, here's the gray is our CPU structure. We have 2 GPUs that we can fit into that machine. The parts that we found really enhanced our performance. We didn't port everything to the GPU. We just ported the most important bits. The velocity rescaling to stabilize the dynamics I told you about is on the GPU. We keep track of the interparticle separation matrix, right, on the GPU. This is really the bottleneck to the whole system, because this is a big matrix. And I think the NVIDIA and the AMD GPUs have 1.5 and 2 gigs of memory on the GPUs, respectively. So I know there's some people from NVIDIA here, so if they're interested in letting us play with a Tesla, that would be cool, because I think those have 6 gigs. Then we run the frozen Gaussian dynamics on the GPU. We evaluate the Leonard-Jones force field terms on the GPU. This is probably the most expensive part of the whole process, as is often the case for molecular dynamics. We do the collision detection. We maintain the velocity autocorrelation for the sonification in real time on the GPU. And then after every time step, we ship out data that we need for rendering. And we use 1 GPU then just to do the graphics rendering. So 1 is all compute, 1 is graphics rendering. The FFT is also done on the GPU because that was extremely cheap, almost no time. And then everything associated with shipping the data out to the artists that are actually making the sounds is then done on the CPU as well. OK, so I'm just about finished, and I just wanted to say, so that, as I said, this started as a public engagement project, and now it's become, we kind of have a pretty state-of-the-art interactive system for quantum molecular dynamics. So now I'm starting to think, well, could you do some real science with this? So what we find, when we do this, we don't just do a performance. We also set it up as a public installation, and people love it. Like the average residence time in the installation is something in the order of 20 to 30 minutes. Like people just sit in it. And it's not even a game. It's just abstract representations of your force field with particles. We haven't incentivized it at all. So I'm starting to think, could we actually do some real science with this? So I don't know if anyone's been reading any of the research coming out of David Shaw's research lab. So David Shaw built a supercomputer called Anton to run unprecedented timescale molecular dynamics. And he actually was able to fold a bunch of small proteins with no approximations, just folded them through sheer compute power. And what I'm wondering is, as I've watched crowds interacting with the system we've built, if we simulated real proteins, I think that the intelligent entropy of a crowd might actually be able to explore the parameter space of some of these proteins in really interesting nonlinear ways. And I want to test if a crowd, what I'm calling the intelligent entropy of a crowd, could actually manage to fold some of these small proteins. And I think we actually have a system where we can start to test that. And that would be super fun. So I mean, if you read how these guys think about proteins folding, they think about it as proteins fold rapidly because random thermal motions cause conformational changes leading energetically downhill toward a native structure, which is like an energy funnel. They think of it as an energy funnel. A crowd is kind of like a thermal bath, but with some intelligence. So they can perturb things randomly, but they can also guide it here and there. So I think it's an interesting thing to consider. If we could maybe fold a protein a lot faster with a crowd than Sean needs to use God knows how much electricity with his supercomputer. And so maybe you think that's crazy, but I mean, the University of Washington has something called the Center for Game Science, and there's a guy called David Baker there who has just a little sort of screensaver application to fold proteins. And they recently had a paper in the Proceedings of the National Academy of Science, which is a journal that I read. And they found that people playing the game were able to find a different protein folding pathway that their program wasn't able to find. And so I think we have a new interface for maybe looking at some of those questions, and I'm kind of thinking about this. So I'm going to do the demo now. In closing, I want to summarize. So I think guided by some algorithms and mathematics from quantum molecular dynamics, we've developed a rigorous algorithmic and mathematical framework for modeling humans as interactive fields. So we kind of have a new HCI experience, right, where users' energy fields are embedded in a quantum MD simulation. We couldn't have pulled this off unless it was, as I've told you, as I hope you believe, like if we hadn't done the GPU acceleration, we couldn't have pulled off a fraction of what we've been able to do, especially given that we have to do it with something that's about that size, because we have to put it in a flight case to take it places. We've developed pretty flexible software to do all this, where everything's modifiable in real time, and it can actually talk to a 7-sensor depth capture system for 360 tracking, which as far as I know is amongst the few 360 depth capture systems that are actually adapted for large spaces. And I think there's more interesting stuff to do with this technology. So I'm going to switch over to you guys. Oh, yeah. So if you're interested, like Nobel Prize winner John Polanyi was, you can Google danceroom spectroscopy. There's a website that has information about it and links to all those crazy stories I showed you that people have written about it, and kind of give some information about how it works. So we will switch over to, yes, you guys. So it should just be, can we turn the lights down a bit? You getting anything? There we go. Okay, so this is 8,000 path integral particles, which is about what we're able to do with good interactivity. So I'm going to go in the space, and I'm going to vibrate, and you're going to hear my vibrations. Got that FFT on? Turn me off, Phil. So that's actually the Fourier transform of the quantum dynamics simulation. You have to do a few oscillations before the FFT can phase lock your frequency. So now we'll show you the grouping algorithm. So this is the invisible simulation that's running under the hood to do some of the sonics that you hear. So this is what's going on. This is so if I move, it's keeping track of my centroid and is tying it to a chord that Tom has pre-selected on his machine. And so as I navigate the space, you see now the group will dissipate. Whoop, I'm still in the simulation. And then when I come back in, it will pick me up as a group using the stochastic evangelical conversion algorithm. And as I move through the space, it will map my motion to some instrument. And so you can compose a whole dance show this way, right? All the dancers can be mapped to different instruments, and their motion in real time is actually generating the sounds that you hear. You have to be careful with dancers because you can actually hear exactly when they're out of phase. And they can say, I'm not out of phase, and you can say, I think your vibrational spectrum will show otherwise. Okay, so you have to be very careful with professional dancers using this technology. So on that note, I'm going to close. I can take any questions, and then if anyone wants to have a go in the lunch break, we'll just let it here. Just the only thing is be careful. We were playing with it earlier when we set it up, and you have to be careful of this. You don't look at the screen and fall backwards. Okay, so yeah.